As a software engineer or a developer or an architect, why should I bother look at these tools? Why do I need to use them? And how code looks like when it's written for streaming engines. So these are the questions I will try to answer today. And this talk relates a bit with the previous talk, which was more focused on Azure and how you deploy applications for streaming. So, but before that, let me introduce myself a bit and shortly. I'm a software engineer at Liveband. I'm part of the fast data team there. We are actually working with big data tools like Apache Spark. We are contributing to open source projects. We support customers, and part of this experience I will try to share with you today. Also, every part of the code I would demonstrate in this talk is available on GitHub, so you can access it there after this talk. So there is a lot of stuff to talk about, and about streaming engines specifically, but today I will give you some background for the history of streaming engines, some key concepts, and what do you need to know when you evaluate such a tool. And then I will close this session with some specific tool like Spark and its support for Spark streaming. So there's a lot of stuff, and stay tuned. I don't know who likes history. I used to hate it, but sometimes it gives you some lessons about how things evolve. And the reason I will give you some background is to answer the first key question, which is why streaming? So a few years ago, things started to look a bit complex in terms of processing data, because popular applications like Facebook and Instagram created the need for processing large volumes of data. And it was then when people tried to look at how they can process this massive data and how they can create meaningful results out of them. So it was then when two really important papers were published from Google, and one of them is the Google File System paper and the MapReduce paper, who actually pushed the initiative for creating tools for processing massive data sets. So after a lot of effort, Apache Hadoop emerged around 2006, and a large ecosystem was built around it. And the basic paradigm this tool was based on is MapReduce. So a really short introduction to MapReduce, just to give you the basic understanding of how this tool works. So in MapReduce, you have your data split, and you actually may deploy them on different nodes. You apply a map function on top of this data on each node, so you can transform them in some meaningful sense, and then you actually shuffle the data using some key or something like that, so you can collocate them on each node, and then you apply a reduce function. So this generic distributed approach for computation is the foundation for Apache Hadoop and most of the tools that do batch processing today. Of course, there are some pros and cons about it, some advantages and disadvantages, and one of the major of them is that batch processing takes time. So another thing is these tools were built with throughput in mind. So you cannot achieve also latency requirements, which are often appear in many use cases out there. Of course, there is some great benefit. You can always process your data and get the best accuracy from them. because you actually have them all. So besides Hadoop and these batch processing tools, also the NoSQL data movement created the environment for processing efficiently large volume of data and actually to solve business problems, because at the end of the day, what really matters is business problems. And this was also possible because of technology achievements like having cheaper memory, more CPUs available, cloud, and all that advancements. So, fast forward to today. Besides the tools, we have to look at the business side. So many of the companies today, and really the disruptive ones, try to do two things. First of all, utilize streaming, and then also utilize machine learning so they can be very competitive. And the reason they do that is they need to decide sooner for the same things the competitor also tries to decide about. So this also is true not only for these companies like Google, Amazon, and it's also true for smaller ones. So we see a lot of customers on the field who try to migrate from traditional architectures to something more streaming related. And so this brings us to fast data instead of big data. So you will see this term more often lately. To back up my arguments, I will provide you with some numbers. This is a report from OpsClarity. OpsClarity is a company which monitors tools like Kafka, Cassandra, with real-time metrics. And in a recent report there, they found something that is really becoming a trend right now. So that is that companies try to move their architecture from traditional batch processing tools based to something more like streaming based. So 90% more or less of the people and the customers want to move to that direction. And the problem with that is that many of them don't have the know-how or they can deal with the complexity of those tools. So you can find many other reports out there from other companies as well who state the same thing. The things are moving fast for streaming architectures. And you can actually access that report and many others. They're freely available. So that's all with history. So hopefully you understand now why we need to move to streaming. And after that, I would like to introduce some key concepts around streaming, so you can get a lot more understanding of how streaming works, and actually you can then start your own adventure with streaming. A stream is just a flow of data which comes from a source and ends to a sink. Usually you want to apply some operations on a stream, and this stream can be finite or infinite in size, which also means bounded and unbounded data. So also we define stream processing on a stream, which is again can be on a bounded or unbounded data stream, and usually you don't have all the data available. So processing is this box between your source and the sink. And you may also have the case that you have multiple streams that you want to process in parallel. And this processing can be like connecting to streams, providing some feedback from one stream to another, like having circles. And it can also be like that data transformation, applying a map function, for example, getting a string to an integer or something like that, depending again on your use case. And also it may mean like storing your data somewhere, like your database or distributed file system or something like that. And the key concept here is, from the diagrams you have just saw, is the graph. So a graph actually represents your operations on the stream. So in this example, I just have my data flow from a distributed file system. I apply a map function, then I do some reduce, and then I store my data either to, again, back to my distributed file system or the database. So you just keep in mind that the graph is the basic abstraction here. And then I may want to split my stream and actually apply this map operation in parallel. For example, I may have two nodes. One applies the same operation. And again, I need to also split my data. And this is possible with a partitioner. So I may have a criteria here which says, in a round robin fashion, I want to split the stream. And this is needed because you may need to process a lot of data, which is not possible with one instance of my operation. And combined with that idea, you also need to provide some abstractions about where things run and how things run. For example, I usually put my code within a task, and then I ship the task on each node. And then I have many instances of each task on each node. And these abstractions need to be implemented more or less for every streaming tool. And the basic idea here is I write my code, then somehow this is shipped to on each node, and then my code is executed. And the key element here is that I need to run my code close to the data. In big data, moving data is a bad thing in general, and the best practice is actually to ship the code and run it as close as possible to the data. So, compared to stream processing, batch processing, we saw before with Hadoop, is processing done on a finite data set. And there is a lot of discussion about batch processing and stream processing and how this is implemented with batch and streaming engines. Actually, the truth is that those tools look more or less the same from the view that you can actually emulate one with the other. For example, it's easy to run streaming processing with a batch tool. And that is because you can actually split your stream, and for each part of for each split, you can run the batch engine. And the key result here is that you can actually have one engine. And that engine so far is like the state of the art right now is that you can use a streaming engine for that, for both batch and stream processing. So you also have your code, and this is what we mean when we say I have written a streaming application, and your code actually creates the streams and applies your stream processing. And the key difference between common streaming engines and streaming engines for big data is that besides the common API and common functionality, it provides you with a rich ecosystem around it for doing a lot of things, like machine learning, graph processing, complex event processing, and provides you with key features for fault tolerance, scalability, and provides you also with key functionality for storing and retrieving your data from different sources. And how that fits within the enterprise architecture, streaming engine, the answer is that usually is part of a big data system. And a big data system is has at least two components. One it's the distributed file system, and the other is the processing engine. And usually it can be either a batch processing engine or a streaming engine. And this is part of the analytics pipeline, which again is part of your enterprise architecture. And usually your analytics pipeline is connected with other parts of your architecture, which is like your microservices component or similar components. So let's have a view of what you should look for when you design a streaming engine. And these features I will talk about are more or less important also when you compare tools. So one key feature every engine, a modern engine should have is strong consistency. And this should always be implemented within the streaming engine. So the description of strong consistency is shortly what will happen with my computation when something fails. So your streaming engine must make sure that computation is done correctly. For example, if I have a counter and I count something, and I should expect that the count value is correct, even if any of my machines fail. Of course, there is a lot of history behind this thing to be done correctly, but the important thing to keep in mind is that should be provided by your engine. Also, you need to have good semantics for integrating time, how you can manage late data. For example, if you have an application where you have a window of time and you say that everything with that window is the data that really are important for me, and something comes late for some reason because of some network delay, you need to have the appropriate functionality there at the API level so you can manage that data. And again, you need to have a lot of other stuff like supporting multiple languages and also SQL and many other things at the API level. Other things are how things are executed, how I can provide elasticity for my jobs, how I can tolerate high throughput or low throughput within my job, how I can actually manage that stuff at runtime. And there are many other things like does my streaming engine support bots and streaming at the same time? Because usually at the field you see different use cases with different requirements. Also, it's important to be able for my streaming engine to support local state. Local state is a very key feature because in real life situations you need to store state within your streaming engine. For example, if you have a user, if you support user state and you want to keep some meaningful data related to your users as you process your streaming, your flow, then it's important to have some feature there to manage this state. And this is possible either locally on your file system or through a database. And many tools out there do support that. Another key feature is backpressure. Backpressure is something really important for every streaming engine because otherwise things will start getting very messy. And all the state-of-the-art engines out there more or less support backpressure. And I can think of many other key features, but this list is good enough for you to actually have an eye on, and then when you try to use a tool, just check if that tool supports and what its support for these things. That's why I also provided this list as a reference as well. So moving a bit forward, I will provide also a few other key concepts we will see shortly in code. So the most recent advances in streaming right now is due to some seminal papers at Google again. And so based on these papers, I will give you some basic abstractions and concepts so we can understand why the API of this engine is formed the way it is right now. So when you do streaming processing, you have actually two options here. One is process your events one by one, or actually aggregate them and do some processing based on some window of time. So event aggregation actually leads to this idea of windowing, and you actually have to also use some notion of time. There are mostly out there you will see two types of time. One is the actual time the event happened, and the other one is the time we processed the event within our engine. Ideally, we would like to have the same timestamp for both the event time and the processing time, but this cannot happen because you always have some delay between the time something happened and the time you processed. So in terms of windowing, you can have two types of windows. Like one of them is tumbling window, where you actually split your streams in non-overlapping parts, and you consider these areas for processing. And the other one is you can move your window on top of the stream, and this leads to more smooth processing. Another key concept is watermark. A watermark is a timestamp which says every data you have seen up to this timestamp refers to this window, and you don't expect any other. You shouldn't expect any other data before that timestamp. So if you see any data with a timestamp which is smaller than that timestamp, it means that this data is late. And then you have somehow to you have to find a way to either discard this data or integrate it within your computation. When this computation is going to take place, this depends on the concept of a trigger. A trigger actually triggers the computation of the window. And all these concepts I just described very shortly are realized through the Apache Beam project, which is the open source version of Google's Dataflow. Google's Dataflow was the project which actually introduced all these concepts. And it's becoming the standard API for streaming. And of course, it needs to be improved over time, but at least now it has a lot of attention. There are a lot of streaming engines for big data out there. Every one of them deserves a series of presentations and a lot of talk. But I will just give some hint for which to choose. For Fling, for example, which is at the top of this list, I would say it has lately drawn a lot of attention, and it's a good candidate for low latency applications and has the best match to what I just described about these state-of-the-art concepts. Also, Apache Spark is a very popular, if not the most popular right now, streaming engine, and it should be used for many use cases when you need mature libraries and mature functionality to be provided, either for machine learning or SQL processing or graph processing. And at last we have Kafka Streams, which is part of the Confluent platform, and it's really good when you get your data and then you want to do some simple transformations and then write them back to Kafka. These are just some recommendations. It's really hard to choose the right tool for the job, but the basic recommendation is choose the right tool for the right job and do it right. So now I will move to Apache Spark as an example tool. So very briefly, Spark is a distributed computing framework for doing distributed computations based in memory, and actually it uses caching of data for speeding computations. The key concept here is the RDD, which represents actually a bounded data set. And you can think of an RDD like a distributed collection, which is immutable. And on this collection, like for example, you can imagine that like a Java list or something, where on that connection you can actually apply transformations and also actions. The difference is that transformations are lazy and they don't trigger any computation on the cluster, while actions actually have an effect and trigger computation, and actually something is executed on your cluster. And also there are a lot of operations that involve shuffle. We saw shuffle at the MapReduce paradigm, so shuffle is something you cannot avoid in general. The basic model how things work in Spark is you have your code, which is your driver program. You create an object there, which is called Spark context, which manages all your work and your interaction with a cluster. So your code there behind the scenes negotiates with a cluster manager for resources, and then your code, again behind the scenes, sends your code to run on different nodes within some executor, and your code actually is wrapped inside a task. And this is very shortly the basic model of execution in Spark. Spark has a lot of components for different things. You have a basic component for doing SQL, also streaming, which we are going to describe next, machine learning, and graph processing. And all these stand on top of the Apache Spark core functionality. So the hello world of big data is word count. So in this basic example, where I will try to count the number of occurrences of each word. So what you do here is create a Spark context at the top, and then I actually create RDD out of this text, and which is shown next after the Spark context creation. And then I simply try to split the lines and get the words, and then I will try to count how many words I have in my text. And this is a very basic example, which is usually used for introduction for every big data tool out there. So Spark supports all the key features we described earlier in some way. So I suggest you read a bit the tool page. And let's move now to Spark streaming, which comes in two flavors in Spark. One of them is the more mature API they have, which is the dstream API, and is implemented by splitting your stream in small batches. And the second API, which is more experimental, it is now under development, is the one that sees the stream as an unbounded table and hides all the details of streaming from the end user. For production, I would recommend the first one, since structured streaming is now in alpha mode. So the first mature API, the stream API, based on some batch interval, splits the stream as I described earlier, and this batch duration is configured only once. So there's not much flexibility there. But again, it provides exactly one semantics with the appropriate configuration. And also, you have the benefit that you get all the transformation actions at the API level you have with the RDD. You can get it with the dstream API as well. So this is really important. And compared to the dstream API, the Spark structured streaming API builds on top of Spark SQL and gives you the capabilities of SQL, so you can actually create the usual SQL queries on top of a stream. And this is really interesting because many use cases out there need to do some kind of SQL queries on top of your data. And this is really useful for data scientists as well, and many people there who really don't want to get into the details of streaming. And they shouldn't, actually, because the streaming engine should hide all the details. And also, at this point of time, it supports HDFS and S3 as source and sinks. And in general, its contract is to have replayable sources and independent sinks, which means that instead of having a transactional source or sink, you can implement the same semantics exactly once, having your source being replayable, which means pick whenever I want to replay again the data from the sink, and also having independent sinks, which means I can reapply the same computation at the sink, store, for example, the same record on the database without having any difference at the result, which means actually overwriting my record on the database. This may sound restrictive, but this is the contract right now for this to be for a source and sink to be compliant with it. So when something is computed with Spark structured streaming, you have two options for the output mode. You can send your data with complete mode, which means everything that is calculated, again with the previous computations, is stored as a whole again at the sink. Or you may use append mode, which actually only appends the latest results to the sink. What is not yet there from the state-of-the-art things we discussed earlier is actually support more sinks and sources, because many use cases need more than just HDFS and S3. You need watermarks, which are not there yet. Late data management is not yet implemented, but there is a lot of work there for that under development. Also state sessions. State sessions, I didn't talk about them, is when you also you want to keep state for your users, and you want this to expire at some point of time. This is really useful when you have an application which keeps user state. And this is a key feature also not implemented in Spark streaming. So this is how it looks to write a job with the dstream API. You simply just again create some Spark context and a streaming context. Actually, you start with a streaming context, and you could also provide the Spark context, but this is not necessary. And then in this example, I use some socket-based stream to feed to feed the Spark streaming. I also defined different types of windows, and I do some very limited computation there. I just report the maximum value over some time, which is different for a dumpling window compared to a sliding window. Also, you can find these examples and you can run them by yourself from GitHub. I just want to give you the idea of how things are translated to code. So they are not far from theory, and theory and code are really close in these systems. So again, if you want to also integrate checkpointing, which means if something fails, my driver fails, I can restart my job, then you have to follow a different convention and wrap all your operations, all the transformations and actions you do to your data within one function and put that in one specific call they have there for creating the streaming context. So before I show you an example about Spark streaming, Spark structured streaming, the basic processing you can do with Spark SQL looks like this code snippet. So you just create a Spark session, and then this object internally creates a Spark context again, and then you can provide some schema for your data, and then you can have operations like transforming your data or doing some SQL processing. And transforming this Spark SQL processing to its streaming counterpart, it's really straightforward. You just have to actually change a few of the API calls. So the target here is to have the same code for batch and streaming. And this simplifies things because you don't have to think about two different APIs, two different code bases, and also involve two different teams for large deployments, for example. And this really matters for big projects. So that's it from me. Thank you.
So Stavros will take some questions. Anyone? Yes?
Hello, thank you for your talk. I have a quite silly-minded question. Two questions, in fact. The one is, when you, in the deployment slide, the smallest Spark cluster we can make is a 4-node cluster?
Actually, you mean for production use or just for playing around with Spark?
For production use.
For production, usually it depends on your data set. So actually, the best practice is to put your data set in memory, because Spark is optimized for that. So you have to think about, this is a very common question, and customers do ask that a lot. So you have to evaluate your cluster against your data set. If I have 1 terabyte of data, then I have to think about my cluster manager, if it's going to be on Yarn, or if it's going to be Mesos, or if it's going to be standalone. If it's going to be like, for example, Yarn, then you have to think about how things are executed, how much memory you have on each machine, and how many machines you need to put your data set in memory. And you have to think about operating system memory, how much you need for that, and for other processes running on that machine. So it really depends on your data. That's
so you have to think at first if you are running on a Yarn cluster or you have a Mesos coordinator. Okay, thank you. And the other one is, as far as I have understood, once you load your data from your whatever data store you have, you create the RDDs, you store them somewhere in a DFS, and then you execute, transform, and whatever to store them to the sink.
No, actually, you have your code, which actually says, it's a blueprint, says how you're going to, what you need to do, like how you're going to transform things. And then you ship that to the engine.
Yes.
I described it a bit in a simplified way, anyway. So you ship that on your nodes, and then this transformations and these actions are realized there. So then at that point, the code, when it's on the nodes, knows how to actually retrieve the data and how to, for example, interact with HDFS to load the data in memory, and then in memory things are computed. That's the idea.
Right, and then when you are going to, all the transformations and the computations are done in memory, and then you write them to the sink, which is, again, a DFS?
It can be anything. It depends on how, what the capabilities the tool provides for you. For example, it could be like S3, can be, again, Kafka, can be Cassandra, it can be, there are many, Elasticsearch, it can be anything.
So for example, I have, for example, a classic RDBMS. I load the data, I create the RDDs, then all the worker nodes load them and make computations, and then store them to a Kafka cluster or another database or wherever we want. Okay, thank you very much.
No problem. Welcome.
Next question.
Hi, Stavros.
Hi.
I have a kind of maybe my question is too specific, I apologize for that. In my company, we use SparkML. And so we have a batch process, we create a model, and we save it in S3. And we wanted to be able to serve that model in a low latency way, like to be able to query something, ideally a web app, and that will use the model and get back an answer. Namely, it's a classification problem. And what we had as a problem is that it's quite slow. We used like a play app that would load the model from S3 and serve it. My question is that can in some way Spark streaming help on that? Where does exactly Spark streaming sit in regard to SparkML? Can they like be combined and have it in another way, in like serve a machine learning model in a low latency way?
Yeah, actually, this is a very common problem, and there is a lot of work done right now by IBM for structure streaming and machine learning. So there are a lot of things that will come, next year. And a common solution to that is use Spark for training your model, and then Fling for serving the model, because Fling has this attribute of being fast with sub-second latency. Or you can again choose a parameter server. I don't know if you're familiar with the concept.
No, not
there are highly optimized servers for serving models. But the problem is there is no generic answer to this problem, because models in machine learning are different. So you may have really big matrices because that's the result model you have, or you may have a very small regression model. Those are different stories. So you don't have one solution for everything. So one option is what I just said. I mean, train your model with Spark. How you do that, it can be like batch processing, and then serve it with Fling or some other tool that's really for low latency. This is a common story, for example.
Okay. Fling can do that through a web API or something, or it's
a connector or something. You can connect to that.
Ah, okay. Okay, thank you.
Or you could even have a real-time storage for that. You can use, I don't know, Splay would be the best, but it can be optimized for that. We can take it offline if you want to discuss more.
Maybe I would appreciate that.
No problem. Yeah, if you want. Yeah.